5. Sitting by my father for 1,000,000 miles, picking up old stories on the ride. I've been counting shadows to the beat of the radio. I feel like a baby when I sleep, and then you come to me. If we can keep the fire burning till I'm coming home, then maybe I won't have the need to let the engine run. 'Cause in the morning, in the night, maybe we can hold each other tight. We can keep the fire burning for a while, babe. Keep it wild. 'Cause in the morning, in the night, maybe we can hold each other tight. We can keep the fire burning for a while, babe. Keep it wild. Too many times I've drifted away. Keep it like a shadow in the sun, having no ownership in a day. Keep the fire burning.
First, please watch the video of Professor Mosalam's lecture. The title is Bridge Rapid Assessment Center for Extreme Events. Let's get started.
Good morning. My name is Khalid Mosalam. I am a professor at University of California, Berkeley. I am also the director of the Pacific Earthquake Engineering Research Center. My presentation today is about Bridge Rapid Assessment Center for Extreme Events, or in short, BRACE2. The outline of this presentation is Peer and BRACE2 motivation, data and global model of Hayward Bridge, damage versus bridge operation actions, system ID of Painter Street overpass, and work in progress and contributions. Peer is a university, government, professional, and industry alliance. It consists of 11 core institutions. UC Berkeley is the headquarters, and 10 other institutions. Also, it includes 9 educational affiliates. Peer combines the resources of major research universities in Western United States, where earthquake hazard is large. The expertise within the Peer Center are geohazards, structures, networks, experiments, analysis, and monitoring, including artificial intelligence. The mission is focused on resilient design for extreme events based on integrated performance-based engineering. Peer focuses on developing several enabling technologies for analytical simulation using OpenSeas, hybrid simulation using OpenFresco, and also maintaining several databases for ground motion, PeerHub, ImageNet, structural performance database, seismic performance observatory, and also maintaining our technical report series, which currently has about 345 reports. So now I will talk about the motivation and need for BRACE2 research. The California State Highway System includes a wide variety of physical assets in 4 primary categories: pavement, bridges and tunnels, drainage, and transportation management system. BRACE2 focuses on bridges. We all know that the probabilities of expected earthquakes of different magnitudes in North and South California are high, and these high probabilities, together with the importance of the state highway system, raise issues related to the annualized economic loss, and also require having a monitoring system for proper assessment of such losses for achieving economical resiliency of the state of California. About $25 million have been invested in strong motion instrumentation over the past 20 years. That led to 16 toll or major bridges to be instrumented, also 66 regular bridges, and having 33 geotechnical arrays. So there is a need to demonstrate that instrumentation can evaluate bridge conditions immediately following an earthquake, and BRACE2 will help response efforts of maintenance and post-earthquake investigation team. The Bridge Rapid Assessment Center for Extreme Events, or BRACE2, is simply a data-driven structural health monitoring center. The objective is to develop a data and simulation framework for real-time rapid and near real-time comprehensive assessments of Caltrans, California Department of Transportation, designed and operated bridges, taking advantage of bridge sensors for condition assessment following earthquakes. So these sensors are typically accelerometers, where data is collected and then the data is used for vibration-based structural health monitoring. On the other hand, one can conduct vision-based structural health monitoring using images and videos. This type of SHM is not discussed in this presentation, and we're only focusing on the vibration-based structural health monitoring. When data is collected, they are processed, and then decision is made whether there is damage or no damage, and that will lead to rapid or detailed maintenance reports that empower the maintenance crew to know what has happened following an earthquake event, such that maintenance operation or reconnaissance work can take place more efficiently. In BRACE2, in this initial phase, we consider 5 bridges. The first bridge is the only one that is monitored in real time, where data is streamed to BRACE2 in real time. This is what is called the Hayward Highway Bridge. It's actually the intersection of highways 580 and 238 in Northern California. There are 4 other bridges that we develop the necessary models for, and we make use of historical data for these 4 other bridges, but not in real time. These are the Meadowland Bridge, Painter Street Overpass, Crowley Lake Bridge, and San Bernardino Interchange. These 5 bridges are located geographically in a distributed manner within the state of California to be a representative set of the different bridges in California. The centerpiece of the work in BRACE2 is the Hayward Highway 580-238 interchange, or in short, the Hayward Bridge. It has 22 sensors on the superstructure, and also has about 10 sensors for the geotech array for a total of 32 sensors that are monitored in real time, and data is streamed in real time to BRACE2. The core components of BRACE2, at its center is the decision-making platform, or DMP, which receives data from the Hayward bridge and its geotechnical array accelerometers in real time. This is done in collaboration with California Geological Survey, where we receive not only the process data, but also the raw data in real time. And together with component modeling, which determine the component limit states, we compare these limit states to the demand from the data, so we can inform Caltrans in real-time rapid assessment the recommended actions. Another type of assessment uses the global bridge modeling and several model updating techniques, including machine learning in the decision-making platform. With this global model and the data and the component limit states, we have near real-time comprehensive assessment, which is also passed on to Caltrans for more in-depth assessment, but it is not done in real time because running the global bridge model for the recorded ground motion consumes some time. The reason of having the raw and the processed data, such that if there is any delay in receiving the processed data from CGS, we can work on the raw data and process them ourselves within BRACE2, so we can reduce any such delay. So the work with CGS led to having access to the data in real time for the Hayward Bridge, and the work in BRACE2 started in August 2020, and by March 2021 we have that real-time access. And since March 2021 until very recently, we have received 24 data sets. Each data set typically is received within 1 minute from the end of the recording. The number of these events that's transferred to the peer server that's used for BRACE2 is increasing with time, as you see in this plot. And for effective future operation within BRACE2, we are working on automated data processing, and all data, as I mentioned, are received within 60 seconds. The difference between processed and raw data in terms of their delivery is about 5 to 6 seconds. The Hayward Bridge Global Modeling uses the state-of-the-art modeling techniques within OpenSeas for modeling the columns using nonlinear beam column elements, for modeling the cap beam and the bridge deck using elastic beam column elements, for modeling the in-span hinges with nonlinear springs, and also for modeling the abutments and the soil structure interaction, which is still work in progress using nonlinear beam column pile elements together with different soil springs in different directions. And finally, the damping is being identified from the data and used in the global model. This shows some details of the octagonal and wide interlocking column sections from the as-built drawings, and we use the different constitutive models that are available in OpenSeas for the reinforcing steel, for the concrete, whether it's confined or unconfined. We also took several cores from the different columns of the bridge, and we are using the material properties from these cores for compression and tension as the material parameters of these constitutive models. This shows the in-span hinge model details in the longitudinal spring, for the longitudinal spring, the transverse spring, and vertical spring. And we also have similar modeling for the abutments, again in the longitudinal, transverse, and vertical directions. Most of these are not new models. These are available models in the literature or in Caltrans design specifications, and we make use of these state-of-the-art models in developing the global bridge model. Several of the bridge bends at the base or at the connection between the column and the cap beam have pin connections. So we looked at a variety of modeling techniques. For example, M1 are all the pin connections modeled as rigid. M2 is the opposite. All pin connections are modeled as with free rotation about the X and Y axes. Models M3, M4, and M5 are in between, where different modeling techniques are used for these three models for the pin connection. For example, M3 use zero length elements, M4 use zero length section, M5 define properties at specific integration points. These give different level of robustness of the numerical model and the numerical solution. And this is part of model updating and the validation with the data to obtain the best model that is representative to the bridge behavior, making use of the recorded data from the bridge. So here I show you some results for these 5 models, where the numbers in blue show the different error levels, plus or minus, compared to the identified information in the form of the fundamental periods in the transverse, longitudinal, and torsional modes. So this bar chart also shows for these 5 models the percentage error compared to the identified model frequencies. And you see that some models do better than others. So from this investigation, we concluded that M4, for example, where all pin connections are modeled as zero length fiber sections, gave the smallest error for these 3 basic modes of transverse, longitudinal, and torsional mode shapes. Also, when we look at time histories comparison between recorded or measured and computed, there is still room for improvement. The absolute error here for the transverse direction is about 12%. For the longitudinal, still very high, 35%. But there is still some work in progress that is going for the boundary condition, modeling the supports, modeling the pile, the abutments. So there is still some updating is taking place. This is a particular small earthquake that took place in 2018 in Berkeley, and it was felt by this bridge. So this is obtained from dynamic analysis that's conducted using this earthquake. And the computed transversal response is reasonable, but the computed longitudinal response still needs updating and refinement, which we are still working on. The third part of this presentation is related to developing a relationship between damage and bridge operation actions. In Caltrans, there is this document called the First Responder Bridge Assessment Guide, which basically lays out 4 bridge operation actions in this Caltrans First Responder Bridge Assessment Guide. R1 is the action where bridge can remain open. R4 is the opposite. Bridge should be immediately closed due to collapse or major damage. R3 and R2 are in between, where R3 is bridge should be closed and structure maintenance and investigation, or SM&I engineering inspection, should be requested. R2, bridge can be open and also SM&I engineering inspection should be requested. Also in this document, there are several examples of visuals related to the bridge operation actions. For example, the third image from the left is a core concrete crushing and rebar buckling, which will lead to an action related to a bridge closure. From our global model, we can estimate a strain-based damage state. Based on work that was done jointly between Caltrans and Peer, which took place in a workshop back in 2017, these 7 damage states are defined with the description given in the second column here and the criteria shown in the third column. And then the strain-based damage state is defined at different fiber location of the cross sections, whether it's in compression or tension, and the value of the strain. So what we try to do is to correlate these damage states to the bridge action according to the document I just showed you in the previous 2 slides, whether it's bridge closure, bridge opening or closing, and considering inspection to take place with that action. And here you see an example of one of the bends of Hayward Bridge, particularly bend 3, one of the columns of this bend that's shown with this yellow arrow, where you see the 7 damage states that are strain-based superposed on the pushover curve obtained from OpenSees and Abacus of that particular column as a single component. And we also superpose the 4 ranges R1 to R4 from this document. And to make sure we are obtaining accurate values of these damage states, we also use the different definition of a damage state based on the displacement calculations using this probabilistic damage control approach by Professor Saidi and his collaborators at University of Nevada, Reno, and we convinced ourselves that our computed strain-based damage state and they are consistent with other damage states from the work of Professor Saidi. Therefore, these first responder ranges are accurately estimated from these component models. The next step is to combine different components to find the relationship between damage and the bridge operation action, but on the system level. This is still work in progress, where we make use of the available software and the philosophy of ATC, Applied Technology Council document 138, which recently was published. where, for example, this is shown here as a faulty tree for bridge open operation action, where for the bridge to remain open, you have to have acceptable level of component damage and also residual drift that's smaller than a certain threshold. And the acceptable level of component damage will come from having columns within R1, according to the first responder document. Maybe 80% or more of the columns have to be in R1. Also, there has to be acceptable conditions for the in-span hinges, the abutments, and so on. So this developing such a fault tree is still a work in progress. The fourth part of my presentation related to system ID, and I will show you that for another bridge, the Painter Street overpass, which is one of the 4 other bridges we are considering in BRACE2. This bridge was subjected to an earthquake that occurred at the end of last year in December 2021. It's called the Petrolia earthquake. It's a sizable earthquake, magnitude 6.2, but it was far from this bridge. That's why the shaking is not very strong. So here we use this data to develop the single input, single output system identification method using transfer function, where here we identify the damping and the dominant frequency. We also developed or implemented methods that use the multiple input, multiple output. Here is shown also for the same bridge. So one of these methods is observer Kalman filter identification and eigensystem realization algorithm with data correlations. That multi-input, multi-output method help not only in identifying modal frequency and damping, but also mode shapes. And here we see the transverse mode and the longitudinal mode, where also the identified modal frequencies and damping are reasonably consistent with the single input, single output using the transfer function. So the last part of this presentation to talk about work in progress. So what we are currently working on is to use the longitude, latitude, and also the VS30, the shear wave velocity from this velocity profile from the geotech array to determine the hazard curve for design basis earthquake and maximum considered earthquake, and then select a large set of ground motion from the NGA database, so we can use this ground motion together with the global bridge model to run simulations that we subsequently use for machine learning based damage state identification. So basically, now that we have the finite element model available, we just developed that. That's basically the digital twin. So we will subject it to this selected set of ground motion. Then we will form the synthetic data set, which we are going to label for the different damage states. And then we use this for training machine learning models. This will be autoregressive, integrated moving average machine learning, or long short-term memory method, or human machine collaboration. These are different machine learning models that we worked with in the past. And then we use ensemble modeling technique to select the best trained models amongst these, such that during the operation stage, when we have the real bridge, the Hayward bridge, in this case, we obtain data from the sensors, we feed it into this trained model so we can make prediction about what damage state this bridge is experiencing, so we can facilitate the decision making that we pass on to Caltrans. The last piece we are working on is to develop a user interface where one can go and select the bridge amongst the 5 bridges we are considering, and then you can perform a variety of sensitivity studies using, for example, a tornado diagram, which is a deterministic sensitivity analysis, or show mode shapes like transverse or longitudinal, or pull out historical data. This is shown here for Menlo Land, for example, and plot the transfer function for a large set of previously recorded motions using input and output from particular sensors to get transverse mode or longitudinal mode. Finally, the contributions of this work includes real-time access to sensor data from the bridge, particularly the Hayward bridge, definition of damage states consistent with bridge operation actions, detailed global model of bridges, the 5 bridges considered in BRACE2, particularly the Hayward bridge, with capability of model updating, system ID of instrumented bridges, and finally developing a plan for short and long-term activities for Caltrans bridge asset management. If you have any questions, please feel free to email me at mosalam@berkeley.edu.